This is a video about elastic forces. Now, elastic forces, they are a subcategory, I suppose, of restoring forces. And a restoring force is one that wants to restore equilibrium. The most common form that I have of this, the most common form that I'm going to come across, will look like this. If I've got a piece of wall and a spring and a mass attached to the end of that spring. Here's my mass. This is a spring. Then if I take this thing and I pull it outward so that the mass is out here instead, I've now pulled this some distance away from equilibrium, some displacement. It wants to be in this location. This is its equilibrium spot. If I just have this thing sitting out, if I just have this mass sitting on a spring, that's where that mass wants to be, because the spring has its own natural length. I displace this thing by some distance x, and what I see is a force that pushes back. And you know this if you've ever messed with springs at all. I have a force that wants to pull this thing back toward equilibrium. Same thing, if I take this mass and I compress it, I'm going to get a force that points back toward equilibrium. Because the force always points back to equilibrium, that makes that a restoring force. It wants to restore equilibrium. This is an elastic force because it deals specifically with a stretching or a compression. So it's a restoring force that just deals with stretching or compressing. We need a couple of things to be able to get anywhere with this. The block has a mass m. The spring has some kind of a quantity associated with it. And we need to be able to quantify that a little bit to quantify the strength of the spring. So that K is something that we call a spring constant. A spring constant has units of newtons per meter, or force per distance, I suppose. And the idea here is that this is a measure of how springy a spring is. If I have the spring that's in the back of like a clicky top pen, that's going to have a relatively small spring constant. You can think of it really in terms of these units. 1 Newton. You know, a Newton is a kilogram meter per second squared. Acceleration from gravity is about 10 meters per second squared. So 10 newtons is about the weight of a kilogram. What that means is a spring constant of 10 newtons per meter would mean if I take this spring and I attach a 1 kilogram mass, so about 2 and change pounds, if I take this spring and I attach a 1 kilogram mass to the end of it, that spring will stretch by a meter. Now that is not a very strong spring. So 10 newtons per meter would be very weak. If I take this spring, and in order to get it to stretch, I have to attach maybe 200 pounds. So 200 pounds would be something like 100 kilograms, which would be 1,000 newtons per meter. This is kind of my mid-range. A 4-digit number of newtons per meter is going to be kind of a mid-range spring. If I'm looking at the suspension on a car is going to have a mass of, 1,000, maybe 5,000 kilograms, somewhere in that range. Let's say 2,000 kilograms is a decent estimate for the mass of a car. That means 20,000 newtons is about the weight of a car. The weight of a car on the compression or on the springs that make up its suspension should be dropping that suspension, but not by a lot. 10 centimeters is a pretty big drop, but let's go with it. Let's say we get a 10 centimeter drop on suspension based on 20,000 newtons of weight. That means those springs would have a spring constant of 20,000 newtons over 0.1 meter is 200,000 newtons per meter, and that is a pretty weak suspension. You are going to have some off-road fun with that kind of a suspension. So this is just to give you an idea of the scale of what a spring constant should be. So we've been doing forces for a little while now, and it seems like springs would be a very natural item to mess with for forces, but they're not quite. What we have for the spring force, we have force is equal to negative k times x. X is the displacement from equilibrium. K is that spring constant that we've already talked about, and F is of course the force. Now K is a scalar, X is a vector. If I displace my block from equilibrium in the positive x direction, I'm going to get a force in the negative x direction. So a stretch comes with a restoring force that wants to return to equilibrium. If I compress, so a displacement in the negative x direction, then this minus sign assures me that my force is going to point back toward equilibrium. This minus sign is what makes this a restoring force. It just means that my F and my displacement are necessarily in opposite directions because my spring constant will always be a positive number. So why haven't we messed with this before? Well, if I take my spring and I stretch it by 10 centimeters, I'm going to get some amount of force on it. If I then let go, yes, I can find the immediate acceleration, but it starts to accelerate, and now maybe this thing, instead of being stretched 10 centimeters, is only stretched 8 centimeters. Well, if it's stretched a different displacement, then I get a different force, and I get a different acceleration. The spring force is not a constant, does not give me a constant acceleration. If it doesn't give me a constant acceleration, then I can't use all those kinematic equations, the equation 1, equation 2, equation 3 that I've been using, because those assume a constant acceleration. Spring force, that's not the case here, which means for a spring, the sorts of problems that we can do are effectively equilibrium problems. I take this spring, put it vertically maybe, attach a mass to the end. How far does the spring stretch? That is a fair game problem. I would say here is my mass, and the forces that I have acting on this, I would have a spring force acting upward. Magnitude is just kx. I would have an mg acting downward. I would probably say let's count up as my positive direction. And my sum of forces says k times x, where x is my displacement, minus mg equals m times acceleration, where my acceleration is going to be 0, and my displacement will be mg over k. If I've got my car that's dropping 10 centimeters on 2,000 newtons, I'm going to say that's 2,000 newtons. 1, 2, 3 newtons over my spring constant, 200. 20,000 newtons, sorry. 200,000 newtons per meter and that's going to give me my 0.1 meters. So I can get there that way. I'm not going to use this to find the acceleration of a system very much at all because it's not a constant acceleration. I can't do anything with it. I will use springs again when I start to get into energy, but for right now, that's a pretty good example of what we're doing. Now, we don't have to have a spring necessarily. We can have different things that act as a spring. A bungee cord has an elastic force that acts a lot like a spring. If you have certain muscle tissues will stretch in a way that behave a lot like a spring. So this F equals negative kx is not reserved specifically for springs. This is a formula called Hooke's law, and it's one that applies to anything that we can model as a spring.